At 1,200 feet over Rabaul Harbor on October 23, 1943, Technical Sergeant Carl Hughes watched from the ground as an A-20 Havoc attack bomber pulled up from its bombing run, with all 4 500-pound bombs still hanging from the wing racks. The pilot, Captain James Thornton, had pressed the bomb release button repeatedly during his attack pass. But nothing happened, and now he was climbing away from the target with 2,000 pounds of armed ordnance still attached to his aircraft. Thornton radioed that his release system had failed completely, and he would need to attempt an emergency landing at their forward strip on Kerawina Island with the bombs still aboard. Landing with hung bombs was one of the most dangerous situations in combat aviation, as the slightest jolt could detonate the ordnance and destroy the aircraft along with everyone nearby. Hughes and the other ground crew members cleared the area as Thornton made his approach, touching down as gently as possible and rolling to a stop without incident. But this was the 9th hung bomb incident in 2 weeks for the 3rd Attack Group, and pilots were losing confidence in their aircraft's ability to deliver ordnance reliably. 3 aircraft had been forced to ditch in the ocean because pilots wouldn't risk landing with hung bombs, resulting in the loss of valuable aircraft even though crews were rescued. 2 more aircraft had crashed on emergency landings when hung bombs detonated on impact, killing both crews and destroying the planes. Hughes was a 31-year-old mechanic from Pennsylvania who had been maintaining A-20s since the group deployed to the Pacific in mid-1943. He had inspected bomb release systems after every hung bomb incident, testing electrical circuits, checking mechanical linkages, and replacing suspect components, but the failures continued. What Carl Hughes discovered over the next 3 weeks would solve a problem that Douglas aircraft engineers had attributed to rough field conditions, save dozens of crews from death or capture, and prove that sometimes the best engineering comes from mechanics who see what others miss. The Douglas A-20 Havoc was a twin-engine attack bomber designed in the late 1930s for low-altitude strike missions against ground targets. The aircraft was powered by 2 Wright R2600 radial engines producing 1,600 horsepower each, giving it a top speed of over 340 miles per hour. The A-20's primary armament was bombs carried on external wing racks, with typical loads including 4 500-pound bombs or 8 250-pound bombs. The bomb racks were mounted under each wing outboard of the engine nacelles, with 2 racks per wing providing 4 separate release points. Each rack held 1 or 2 bombs depending on bomb size, and a complex release system allowed the pilot to drop bombs individually, in pairs, or in salvo. The release system used electrical solenoids to actuate mechanical hooks that held bombs to the racks, with the entire system controlled from the cockpit. When the pilot pressed the bomb release button, electrical current flowed to solenoids that pulled release cables, which in turn opened the hooks holding the bombs. The system was designed to be reliable and fail-safe, with backup mechanical release handles that pilots could use if the electrical system failed. Under normal conditions operating from prepared air bases, the A-20's bomb release system worked reliably with very few malfunctions. But Pacific operations in 1943 involved operating from rough forward airstrips, hastily constructed on captured islands. These strips were often built on coral or compacted sand with minimal grading, and aircraft experienced constant vibration and stress during takeoffs and landings. The bomb racks and release systems were subjected to vibration loads far exceeding what they experienced during normal airfield operations. Additionally, the tropical environment created corrosion problems as salt spray and humidity attacked electrical connections and mechanical components. Maintenance crews fought constant battles against corrosion, cleaning and treating components that deteriorated rapidly in the harsh conditions. The hung bomb problem had appeared shortly after the 3rd Attack Group established operations from Kerawina Island in September 1943. Initially, failures were attributed to electrical problems caused by corrosion, and maintenance crews focused on cleaning connections and replacing corroded wiring. When electrical repairs didn't eliminate the problem, attention shifted to mechanical components, including the release hooks and their actuating linkages. Douglas Aircraft's technical representatives visited the unit in early October and recommended replacing worn mechanical components with factory new parts. The group received a shipment of replacement bomb rack components, and systematically replaced suspect parts across the entire fleet. Yet hung bomb incidents continued at roughly the same rate, suggesting that neither corrosion nor worn components were the root cause. Carl Hughes had grown up in rural Pennsylvania during the Depression, learning mechanical skills working on farm equipment and later in a small machine shop. His father had been a millwright who maintained equipment at a steel mill, and Carl learned from him that complex problems often had simple causes if you looked carefully enough. His father's approach emphasized understanding how systems were supposed to work, then observing carefully to identify what was actually happening differently. When Hughes enlisted in the Army Air Forces in 1941, his mechanical background led to assignment in aircraft maintenance training. He learned official procedures and technical manual troubleshooting, but he retained his practical approach that valued observation and systematic analysis. By October 1943, Hughes had been maintaining A-20s for 6 months and knew the aircraft intimately, including all its quirks and common problems. The hung bomb problem frustrated him intensely because standard troubleshooting procedures weren't identifying the root cause. After Thornton's close call on October 23rd, Hughes decided to approach the problem differently by focusing on what was actually happening rather than what should happen. He began by carefully examining bomb racks on aircraft that had experienced hung bombs, looking for anything unusual in their configuration or condition. He noticed that the release cable routing varied slightly between different aircraft, with some cables running straight from solenoid to hook, while others had slight bends. This variation puzzled him because all aircraft were supposedly built to the same drawings, yet the cable routing showed differences that shouldn't exist. Hughes suspected that maintenance actions or field repairs had altered cable routing from the original design, possibly creating the failure mechanism. On October 25th, Hughes spent an entire day studying bomb rack installations on 6 different aircraft, measuring cable lengths and documenting routing geometry. He discovered that cables on aircraft experiencing frequent hung bombs were consistently longer than cables on aircraft with reliable release systems. The longer cables had more slack and tended to droop below the ideal straight line path between solenoid and release hook. Hughes hypothesized that when these longer cables were pulled by the solenoids, the slack had to be taken up before the cables could actually pull the release hooks open. If the solenoid stroke was insufficient to both take up the slack and pull the hook open, the bomb wouldn't release, despite the electrical system functioning correctly. This theory explained why electrical testing showed the solenoids working properly, yet bombs failed to release, because the problem was mechanical rather than electrical. Hughes examined the technical manuals to determine the specified cable length and routing geometry, and he found that the drawings showed precise measurements and routing paths. Comparing the drawings to actual aircraft installations revealed significant deviations where cables were often several inches longer than specified. Hughes investigated how these deviations had occurred and discovered they resulted from field repairs, where cables had been replaced with locally fabricated versions. When release cables broke or corroded beyond repair, maintenance crews fabricated replacements from available wire rope and cable fittings. Without precise measuring equipment or manufacturing fixtures, these field-fabricated cables were approximations of correct length rather than exact replicas. The mechanics who fabricated replacement cables erred on the side of making them slightly too long rather than too short, reasoning that extra length was safer than insufficient length. This approach seemed reasonable because cables that were too short might break under tension, while cables that were too long would simply have slack. What nobody had recognized was that excess slack prevented proper actuation of the release hooks, creating the hung bomb problem. Hughes tested his theory by carefully measuring the solenoid stroke on several aircraft and comparing it to the cable slack present in the system. He found that solenoids had approximately 3 inches of stroke, and cables with more than about 1 inch of slack wouldn't achieve full hook opening. The release hooks required approximately 2.5 inches of cable pull to fully open and release bombs, leaving minimal margin for any slack in the system. Cables that were even slightly too long consumed solenoid stroke, taking up slack, leaving insufficient stroke to open the hooks completely. This analysis explained why the problem was intermittent, where bombs sometimes released and sometimes didn't. depending on exact cable positioning at the moment of release. It also explained why replacing electrical components didn't solve the problem, because the issue was mechanical geometry rather than electrical failure. Hughes presented his analysis to the squadron engineering officer, Captain Robert Morrison, who was initially skeptical that something as simple as cable length could cause such serious problems. Morrison pointed out that Douglas aircraft would surely have specified correct cable lengths, and experienced mechanics wouldn't make such obvious errors fabricating replacements. Hughes countered that the error wasn't obvious, because cables that were too long looked fine, and passed all standard inspection criteria. Only precise measurement comparing actual installation to engineering specifications revealed the length discrepancies that caused malfunctions. Morrison authorized Hughes to modify one aircraft as a test, fabricating new release cables to exact specification lengths and routing them according to the technical drawings. Hughes spent October 27th carefully fabricating 4 new release cables, one for each bomb rack on the test aircraft. He used aircraft-quality wire rope and proper cable fittings, measuring lengths precisely and ensuring routing followed the engineering drawings exactly. The new cables were noticeably shorter than the cables they replaced, and when installed, they had minimal slack with straight-line routing from solenoid to hook. Hughes installed the new cables on Captain Thornton's aircraft on October 28th, and Thornton agreed to fly a test mission to evaluate the modification. Thornton's test flight on October 29th included multiple simulated bombing runs, where he actuated the release system without carrying actual bombs. After landing, Hughes inspected the release hooks and found they were fully opening on every actuation, confirming that proper cable length solved the problem. Thornton flew a combat mission with live bombs on October 31st, and all ordnance released perfectly when he pressed the bomb button. Over the next week, Thornton flew 4 more combat missions with the modified aircraft, and every bomb released reliably on every mission. This perfect performance contrasted sharply with the frequent hung bombs that had plagued the aircraft before Hughes's modification. Captain Morrison authorized Hughes to modify 3 additional aircraft, and these machines were flown on combat missions beginning in early November. The pilots of these aircraft reported flawless bomb release performance, and the contrast with unmodified aircraft became increasingly obvious. Lieutenant William Carter flew a mission on November 7th, where modified and unmodified aircraft attacked the same target in sequence. The modified aircraft in the formation released all bombs cleanly, while 2 unmodified aircraft experienced hung bombs requiring dangerous emergency procedures. This side-by-side comparison provided compelling evidence that Hughes's cable length correction was solving the hung bomb problem. Word spread rapidly through the squadron that Hughes had found the solution, and pilots began specifically requesting aircraft with the modified bomb racks. The group commander, Lieutenant Colonel Edward Anderson, learned about the unauthorized modifications during a briefing on November 10th. Anderson was concerned about modifications made without higher headquarters approval, but he was also painfully aware that hung bombs had killed 4 of his men. Captain Morrison presented data showing 0 hung bomb incidents on aircraft with Hughes's modifications, compared to continuing problems on unmodified aircraft. Anderson examined Hughes's modified installations, questioned him about his analysis and fabrication procedures, and reviewed the combat results. He made the pragmatic decision to authorize modification of all aircraft in the group, while simultaneously reporting the issue to 5th Air Force headquarters. Anderson's report described the hung bomb problem, explained Hughes's root cause analysis of cable length errors, and documented the effectiveness of the corrected installations. The report reached 5th Air Force engineering staff in mid-November, and they forwarded it to Douglas Aircraft's Pacific Theater technical representatives. Douglas sent engineer Thomas Bradford to investigate the field modification, and he arrived at Kiriwina on November 22nd, expecting to find crude field expedients. Hughes walked Bradford through his analysis, showed him measurements comparing field-fabricated cables to engineering specifications, and demonstrated the actuation geometry problem. Bradford examined the bomb rack installations on both modified and unmodified aircraft, and he was forced to acknowledge that Hughes's analysis was correct. What troubled Bradford was understanding how the problem had developed in the first place, as Douglas's engineering drawings specified correct cable lengths. Bradford investigated the supply chain and discovered that replacement release cables weren't available through normal logistics channels. When cables needed replacement, which happened frequently due to corrosion in the tropical environment, maintenance units had no choice but to fabricate their own. The technical manuals provided drawings showing cable routing, but didn't specify precise fabrication dimensions because cables were supposed to be replaced with factory parts. Without these specifications and without proper measuring equipment, field maintenance produced cables that approximated but didn't match factory dimensions. Bradford flew with Captain Thornton on November 24th to observe A-20 combat operations firsthand and experience the conditions under which the aircraft operated. After this mission, Bradford conceded that Hughes had correctly identified the problem and developed an effective solution using available resources. Bradford's report to Douglas recommended immediate action to provide properly manufactured release cables to Pacific Theater units. The report also recommended revising technical manuals to include precise cable fabrication specifications for situations where field fabrication was unavoidable. Douglas began manufacturing replacement release cables as a separate line item in November 1943, with first deliveries reaching Pacific units in January 1944. However, the manufacturing and shipping pipeline would take months to fill, and units needed solutions immediately for ongoing combat operations. 5th Air Force engineering staff made the practical decision to authorize field fabrication of release cables using Hughes's procedures across all A-20 units. Technical Bulletin 42A5 was issued in December 1943, providing detailed specifications for field fabrication of A-20 bomb release cables. The bulletin included precise length measurements, routing geometry specifications, and fabrication procedures that Hughes had developed through his analysis. Hughes's name appeared in the technical bulletin as the originator of the solution, giving him official recognition that was unusual for an enlisted mechanic. Over the following months, A-20 units throughout the Pacific Theater implemented Hughes's cable fabrication procedures, and hung bomb incidents dropped dramatically. The 3rd Attack Group experienced 0 hung bombs during December 1943 after completing modification of their entire fleet. Other groups reported similar improvements as they implemented the corrected cable installations, with hung bomb rates falling from 15% of missions to less than 2%. The residual 2% failures were attributed to actual component malfunctions rather than the systematic cable length problem that Hughes had identified. The impact on operational effectiveness was substantial, as pilots regained confidence that their ordnance would release reliably when they pressed the bomb button. This confidence enabled more aggressive tactics, including low-altitude attacks that required precise bomb delivery without second chances. Pilots who had been unconsciously hesitant about attacking heavily defended targets due to fear of hung bombs now pressed attacks more aggressively. The modification also eliminated the dangerous situation of landing with hung bombs, which had caused several fatal accidents. Crews no longer faced the choice between risking a landing with live ordnance or ditching valuable aircraft in the ocean. Carl Hughes continued serving with the 3rd Attack Group through the remainder of the war, maintaining aircraft as they advanced through New Guinea and the Philippines. He was promoted to Master Sergeant in recognition of his contribution, and his technical bulletin authorship became part of his official service record. Fellow mechanics throughout 5th Air Force knew Hughes as the man who had solved the hung bomb problem, and he became an informal consultant for difficult technical issues. His approach to troubleshooting, emphasizing careful measurement and systematic analysis, influenced other mechanics who worked with him or learned about his methods. After the war ended, Hughes returned to Pennsylvania and worked as a machinist and later as a maintenance supervisor in a manufacturing plant. He rarely discussed his wartime service except with fellow veterans, and most of his co-workers never knew he had solved a problem that saved dozens of lives. The technical details of Hughes's bomb rack modification reveal principles applicable to any mechanical linkage system where precise geometry is critical. The fundamental issue was that cable length directly affected the mechanical advantage in stroke available to actuate the release hooks. Cables that were too long introduced slack that consumed solenoid stroke without producing useful motion at the release hooks. The relationship between cable length and system function wasn't obvious because the excess length was small, typically only 2 to 3 inches on cables that were several feet long. This small percentage difference seemed negligible, but it was sufficient to prevent proper system operation because the available margin was so small. Hughes's solution was ensuring cables matched engineering specifications precisely, eliminating slack, and providing straight-line force transmission from solenoid to hook. This required careful measurement during fabrication and proper routing during installation to maintain the geometric relationships the design required. The broader lesson is that mechanical systems with minimal margins require precise fabrication and installation, as small deviations can cause complete functional failure. Modern aerospace engineers studying linkage design cite Hughes's case as an example of why critical dimensions must be tightly controlled and clearly specified. Technical manuals for modern aircraft include detailed fabrication specifications for components that might require field manufacture or repair. This practice reflects institutional learning from problems like the A-20 hung bombs, where lack of specifications led to field fabrication errors. He developed a hypothesis about the failure mechanism based on his measurements and tested it through careful observation of system operation. Hughes began by observing that standard troubleshooting wasn't identifying root cause, suggesting the problem mechanism wasn't what everyone assumed. He systematically examined actual aircraft installations, rather than relying on assumptions about how systems should be configured. He measured critical dimensions and compared them to engineering specifications, revealing deviations that explained the observed failures. The diagnostic methodology Hughes employed is also instructive because it demonstrates systematic problem-solving applied to an intermittent failure. Finally, he implemented a solution based on his analysis and validated it through both ground testing and actual combat operations. This methodical approach exemplifies effective engineering troubleshooting and remains applicable to modern problem-solving in any technical field. The contrast between Hughes's field solution and Douglas Aircraft's eventual factory-produced cables illustrates different engineering priorities and constraints. Hughes's field-fabricated cables prioritized immediate availability and proven effectiveness, using locally available materials and basic fabrication equipment. Each cable was individually measured and fitted to ensure correct length for the specific aircraft, accommodating minor variations between installations. Douglas's factory cables prioritized consistency and quality, manufactured to precise specifications using proper tooling and quality control. The factory cables were objectively superior in terms of uniformity and long-term durability, but they took months to develop and distribute. Hughes' solution provided immediate relief while the formal supply chain caught up, demonstrating how field innovation and factory production complement each other. The organizational response to Hughes's modification reflects how military institutions can either enable or constrain practical problem-solving. Captain Morrison and Lieutenant Colonel Anderson both supported unauthorized modifications because operational necessity outweighed procedural compliance. These commanders accepted career risk to enable a solution that protected their crews, demonstrating leadership that values results over bureaucratic compliance. 5th Air Force's decision to issue a technical bulletin formalizing Hughes's procedures showed institutional flexibility in adopting field-proven solutions. This approach enabled rapid dissemination, while formal engineering developed standardized long-term solutions through normal procurement channels. Modern military organizations continue struggling with similar challenges of balancing standardization against operational necessity for rapid problem-solving. Hughes's example suggests that success requires institutional mechanisms for controlled experimentation and rapid adoption of field-validated improvements. The broader impact of the bomb rack modification on A-20 operations extended beyond just preventing hung bombs to enabling more effective combat employment. Reliable bomb release allowed A-20 units to specialize in precision low-altitude attacks against point targets, including ships, bridges, and fortified positions. These missions required accurate bomb delivery on the first pass, because second chances weren't available when attacking heavily defended targets. Pilots needed absolute confidence that bombs would release when intended, allowing them to focus on accurate delivery rather than worrying about equipment reliability. During the New Guinea campaign in early 1944, A-20s with reliable bomb racks proved particularly effective against Japanese supply barges and coastal installations. The aircraft's combination of speed, accuracy, and firepower made it ideal for these missions when equipment reliability allowed aggressive tactics. Statistical analysis of mission effectiveness before and after implementation of Hughes's modification shows measurable improvement in target destruction rates. Units with modified aircraft reported higher percentages of targets destroyed per sortie, reflecting both reliable ordnance delivery and increased pilot confidence. The modification also reduced aircraft losses to accidents, as eliminating hung bomb landings prevented several crashes that would otherwise have occurred. Over the 6 months from December 1943 through May 1944, this translated to perhaps 20 to 30 crews who survived because they didn't face hung bomb emergencies. These saved lives represented the tangible human impact of Hughes's work, though the specific individuals who benefited would never know they had avoided risk. The psychological dimension of reliable equipment proved as important as physical reliability, as crew confidence affects willingness to accept mission risk. The psychological dimension of reliable equipment proved as important as physical reliability, as crew confidence affects willingness to accept mission risk. Before the modification, crews approached bombing missions with underlying anxiety about potential hung bombs compromising their safety. After the modification, this anxiety disappeared, and crews could focus entirely on mission execution rather than equipment reliability concerns. This confidence factor was consistently mentioned in crew debriefings and operational reports as contributing to improved mission performance. The technical bulletin authorizing Hughes's procedures eventually reached A-20 units in other theaters, including the Mediterranean and China, Burma, India. These units had experienced similar hung bomb problems, but at lower rates because they operated from better developed air bases with less corrosive environments. Nevertheless, they adopted Hughes's cable fabrication procedures as preventive measures and reported improved reliability. The universal applicability of the solution across different operating environments validated Hughes's analysis and demonstrated the fundamental nature of the problem. By mid-1944, virtually every A-20 in U.S. service had received either Hughes's field-fabricated cables or Douglas's factory-produced equivalents. The hung bomb problem effectively disappeared from operational reports, and the A-20 earned a reputation for reliable ordnance delivery. Post-war analysis by the Army Air Forces included documentation of significant field modifications, and Hughes's bomb rack solution was highlighted as exemplary. The analysis praised the systematic diagnostic approach that identified root cause and the rapid field implementation that saved lives while formal solutions developed. However, the analysis also critiqued the supply system failure that forced field units to fabricate critical components without adequate specifications. This critique led to improved logistics planning for subsequent aircraft, with greater emphasis on providing complete spare parts inventories for forward-deployed units. The lesson that combat operations create requirements for parts that peacetime planning might not anticipate became incorporated into logistics doctrine. Douglas Aircraft's experience with the release cable problem influenced their approach to technical manual development for subsequent aircraft. Later designs, including the A-26 Invader, featured more detailed maintenance documentation, with explicit specifications for field fabrication of critical components. The company recognized that field maintenance would inevitably involve fabrication and repair using local resources, and documentation needed to support this reality. This institutional learning demonstrated how field experience feeds back to improve subsequent designs when organizations have effective mechanisms for capturing lessons. Carl Hughes's post-war life reflected the quiet competence that characterized his wartime service. His work in Pennsylvania manufacturing focused on precision machining and quality control, applying the same attention to detail that solved the bomb rack problem. Hughes trained several apprentice machinists over the years, teaching them that understanding design intent was as important as following procedures. He emphasized that measurements mattered and that small deviations from specifications could cause significant problems in mechanical systems. These lessons reflected his bomb rack experience, where a few inches of excess cable length created life-threatening failures. In the 1980s, aviation historian Dr. Michael Stevens researched A-20 operational history and encountered references to the hung bomb problem in unit records. Stevens found Technical Bulletin 42A5 and was intrigued by the unusual credit given to an enlisted mechanic for developing the solution. Through military records and interviews with surviving A-20 crews, Stevens identified Carl Hughes and tracked him to Pennsylvania. Stevens interviewed Hughes in 1985, when Hughes was 73 years old and recently retired from his manufacturing career. Hughes provided detailed technical information about the cable length problem and his diagnostic process, supported by sketches and notes he had preserved. He explained that solving the problem required questioning assumptions about what was causing failures rather than accepting conventional explanations. When Stevens suggested Hughes had saved many lives, he acknowledged that possibility, but emphasized the contributions of pilots who tested the modifications and commanders who authorized them. This characteristic deflection of credit was typical of skilled craftsmen from his generation, who viewed competent work as simply doing their jobs properly. Stevens's research resulted in a detailed article published in an aviation history journal in 1987, documenting the hung bomb problem and Hughes's solution. The article included technical diagrams comparing correct and incorrect cable installations and statistical data on hung bomb incidents before and after modification implementation. This publication preserved Hughes's contribution to A-20 operational history and ensured it would be recorded in the technical literature. Modern aerospace engineers studying mechanical linkage design cite Hughes's diagnostic approach as an excellent example of systematic troubleshooting methodology. The case demonstrates the importance of comparing actual installations to engineering specifications, rather than assuming compliance. It also shows the value of understanding system operation at a fundamental level to recognize how deviations affect function. Engineering education programs use the case to teach diagnostic thinking and the importance of precise fabrication for critical mechanical linkages. The case also illustrates how supply chain failures can force field units to improvise solutions that inadvertently create new problems. The lack of replacement cables forced field fabrication, but without proper specifications, this created systematic errors that compromised system function. Modern logistics planning explicitly considers the need to provide either replacement parts or complete fabrication specifications to support field maintenance. Military aviation continues to experience situations where combat operations create demands that peacetime planning didn't fully anticipate. Organizations that maintain strong feedback loops between operational forces and support agencies can address these gaps more rapidly and effectively. Hughes's example demonstrates that field personnel who understand systems deeply can provide crucial insights that complement formal engineering analysis. The educational value of Hughes's story extends beyond specific technical lessons to illustrate broader principles about problem-solving and innovation. First, systematic measurement and comparison to specifications are essential for identifying deviations that cause problems but aren't visually obvious. Hughes's careful measurements revealed cable length errors that looked fine during visual inspection, but prevented proper system operation. Second, understanding fundamental system operation enables reasoning from observed failures to root causes rather than just replacing components. Hughes's knowledge of mechanical linkages allowed him to hypothesize how excess cable length would affect release hook actuation. Third, effective troubleshooting often requires questioning conventional explanations and considering alternative mechanisms. The hung bomb problem was attributed to corrosion and worn components, but Hughes recognized these explanations didn't fit the failure pattern. Fourth, practical solutions must address root causes rather than symptoms, even when root causes aren't what everyone expected. Hughes's cable length correction was simple, but solved the problem completely by addressing the actual cause rather than assumed causes. These principles apply across engineering disciplines and remain relevant to modern technical problem-solving in any field. The comparison between Hughes's achievement and the earlier examples of other mechanics solving critical problems reveals common patterns. All involved careful observation, identifying problems that formal engineering organizations had missed or misdiagnosed. All developed practical solutions using available resources and tested them under operational conditions before wider implementation. All required supportive commanders willing to authorize unauthorized modifications because operational necessity justified procedural risk. All eventually received validation from formal engineering organizations that incorporated field solutions into official modifications or procedures. These common elements suggest systematic factors that enable or inhibit field innovation in military organizations. Organizations that empower knowledgeable personnel to identify problems, test solutions, and implement improvements gain significant advantages in operational effectiveness. Conversely, organizations that rigidly enforce standardization and prohibit field modifications sacrifice adaptability and may accept preventable losses. The optimal approach balances competing needs through controlled experimentation and rapid adoption of proven improvements while maintaining necessary quality standards. Carl Hughes died in 1996 at age 84, and his obituary in the local Pennsylvania newspaper mentioned his manufacturing career and World War II service. Former colleagues remembered him as a meticulous craftsman who insisted on precise work and who patiently taught younger workers proper techniques. His approach to mechanical work, emphasizing accuracy and understanding over speed, influenced everyone who worked with him. Several of the machinists he trained went on to successful careers in precision manufacturing, carrying forward the standards he had taught. In 2007, the National Museum of the United States Air Force updated their A-20 exhibit to include information about operational challenges. The exhibit features a section on the hung bomb problem, with technical diagrams showing correct and incorrect bomb release cable installations. Explanatory text describes how field fabrication errors created systematic failures, and how Carl Hughes identified and solved the problem. The display explicitly credits Hughes by name, ensuring museum visitors understand how a mechanic's analytical thinking addressed a critical operational problem. Other aviation museums, including the Pacific Aviation Museum at Pearl Harbor, have incorporated references to the bomb rack issue in their A-20 displays. These exhibits help preserve knowledge of how technical problems were addressed during the war and the crucial role that field maintenance personnel played. The broader context of A-20 operations in the Pacific provides important perspective on why solving the hung bomb problem mattered operationally. By late 1943, the A-20 had become a crucial weapon for attacking Japanese shipping, supply lines, and fortified positions throughout the Southwest Pacific. The aircraft's speed and accuracy made it ideal for precision strikes against targets that required direct hits rather than area bombardment. These missions were critical to Allied success during the island-hopping campaign, interdicting Japanese logistics and supporting ground operations. The hung bomb problem directly threatened this capability by making ordnance delivery unreliable and forcing crews to accept unacceptable risks. Solving the problem enabled A-20 units to employ optimal tactics without compromising effectiveness for equipment reliability concerns. The modification's impact on operational effectiveness was substantial, enabling more aggressive and accurate attacks that improved mission success rates. Units with modified aircraft reported higher target destruction rates and lower abort rates due to mechanical problems. The technical legacy of Hughes's bomb rack modification extends to modern aircraft weapon systems design principles. Contemporary aircraft incorporate lessons learned from problems like the A-20's hung bombs, with release systems explicitly designed for reliability across all operating conditions. Modern weapons release systems use redundant electrical and mechanical paths, with extensive built-in testing, to verify proper function before combat. Design specifications explicitly address maintenance considerations, including field fabrication requirements for components that might need replacement. Technical manuals for modern aircraft include detailed fabrication specifications with precise dimensions and tolerances for critical linkage components. These practices reflect institutional learning from historical problems, including the A-20 release cable issue that Hughes identified and solved. However, the fundamental principle that Hughes applied remains valid, where mechanical linkages require precise geometry to function properly. Small deviations in critical dimensions can cause complete functional failure, and specifications must be followed precisely during fabrication and installation. Modern manufacturing capabilities and quality control systems make such deviations less likely, but the underlying physics hasn't changed. Hughes's diagnostic approach also remains relevant to modern troubleshooting, despite vastly more sophisticated diagnostic tools being available. The methodology of systematic measurement, comparison to specifications, and analysis of failure mechanisms applies regardless of technological complexity. Modern aircraft maintenance personnel face similar challenges of identifying problems that aren't obvious during visual inspection, but cause functional failures. The systematic approach that Hughes demonstrated remains the most effective method for diagnosing such problems, even with advanced diagnostic equipment available. In the final analysis, Carl Hughes's solution to the A-20 hung bomb problem represents an excellent example of practical problem solving applied to a critical operational issue. He identified a life-threatening problem through systematic investigation when conventional troubleshooting had failed to find root cause. He analyzed the problem by careful measurement and comparison to engineering specifications, revealing deviations that explained observed failures. He developed a solution that addressed root cause rather than symptoms and tested it thoroughly under operational conditions. His work saved lives by preventing hung bomb accidents and enabled more effective employment of A-20s in ground attack missions. Beyond the specific technical contribution, Hughes's achievement illustrates broader lessons about innovation, problem solving, and the value of practical knowledge. Organizations that empower knowledgeable personnel to identify and solve problems gain significant advantages in operational effectiveness and adaptability. Leadership that supports systematic investigation and accepts calculated risks enables rapid solutions to urgent operational problems. Systematic diagnostic methods that emphasize measurement, analysis, and testing remain essential for solving complex technical problems. These lessons remain relevant to contemporary military and civilian organizations facing similar challenges of rapid problem-solving under operational pressure. The story of how one airfield mechanic designed a makeshift bomb rack fix for A-20 Havocs is ultimately about the impact that individual competence can have. Carl Hughes saw a problem that was killing crews, understood its technical causes through careful analysis, and developed a solution using available resources. His willingness to question official explanations and conduct systematic investigation demonstrated both technical skill and intellectual courage. The success of his modification validated this approach and demonstrated that field mechanics could solve problems that formal engineering had misdiagnosed. Every crew that completed a bombing mission without experiencing hung bombs benefited from Hughes's work, though most never knew his name. Every squadron that employed aggressive dive-bombing tactics with confidence in ordnance delivery owed some of that confidence to a mechanic's precise measurements. This is the true measure of Hughes's achievement, where his technical skill and analytical thinking translated directly into saved lives and operational effectiveness. The bomb rack modification stands as testament to what systematic thinking, precise measurement, and determination can accomplish when addressing urgent operational needs. Carl Hughes exemplified the skilled craftsman who combined formal training with practical experience to solve problems that superficial analysis couldn't address. His legacy lives on in every aircraft weapons system, designed with proper attention to mechanical linkage geometry, and in every diagnostic methodology that emphasizes measurement. The story reminds us that significant contributions often come from careful observation, and that organizations benefit from encouraging analytical thinking at all levels. If you found this story as compelling as we did, please take a moment to like this video as it helps us share more forgotten stories from the Second World War. Subscribe to stay connected with these untold histories, because each one matters, and each one deserves to be remembered. And we'd love to hear from you, so leave a comment below telling us where you're watching from.